Hello everyone. This video is on section 10.5 part 1 titled Solving Logarithmic Equations. So in this video I'm going to be going over a version of the Knewton Alta assignment for section 10.5 part 1. Please understand that the questions I see in this video may not be the same questions that you see when you're working on the assignment yourself. But the objectives are the same, the types of questions should be similar, so I'm hoping that watching me go over several of these here will help you in some way when you're working on the assignment on your own. Okay, so here's the assignment page. You will not see the words preview of, right? You'll just have the title of the assignment. Then you have your mastery bar telling you how far along you've gotten. And then beneath that you have the objectives. It looks like there are 2 objectives for this particular assignment. And then beneath the current objective there is a question related to that objective. And at the bottom of every question you should be seeing a feedback button to send feedback to Knewton if you wish. You will not see the instructor cheat button, right? That will not be there. But you will see a more instruction button, which if you click on this you'll see further reading material or videos related to the current objective that hopefully help you out. Alright, so the first question is on the objective: use the one-to-one property of logarithmic equations to solve logarithmic equations. Alright, so we're going to be using several properties of logarithms throughout this video, throughout this assignment. Now, before I get into this question here, let me just refresh your memory on some of those properties. These were actually brought up in section 10.4 part 1 and part 2 as well. So we're going to be using these properties of logarithms in the other objective. Remember the product property, the quotient property, and the power property. Alright, so I'll refresh your memory of these later when we need them. But right now we are asked to use what they're calling, the one-to-one property of logarithmic equations. So I'll write that here. Now this is very similar to the one-to-one property for exponential equations, right? We saw those, I believe, sometime earlier in the chapter 10 sections. I forget exactly which one, and I apologize for that. But we have the one-to-one property for logarithms. Alright, so that states the following. If the logarithm base b of, say, m is equal to the logarithm base b of n. Okay, so if you can get an equation to look like this, right, both sides are a single logarithm with the same base. Right, see how both have base b. The only way that's going to happen, right, the only way 2 logarithms of the same base are equivalent is if their arguments are equivalent, right, their inputs. So if we have the log base b of m equals the log base b of n, then m must be the same as n. M must be the same as n. Right. And that's huge, right? And I'll put this in a little box here. Alright, so when we're working on questions under this objective, we're going to be using this, right? We're going to try to write both sides as a single log with the same base. So our first example, right, the first question we're given, we're asked to, solve for x. On the left side, we have the log of 343. Now hopefully you recall that when there's no base after the log, no subscript, remember that's base 10. You can write a 10 there if you want, but if there's no base, that's base 10, right? The common logarithm. Equals 3 times the log of x. Alright. So, this does not look like this just yet. Alright. Yes, both sides have a logarithm with the base 10. Cool. But the right side is not just a log. Right? It's a logarithm times 3. Notice in this equation here in the property, both of these logarithms are times 1. Right? There's no 3 or some other number there. So this is where some other properties of logarithms are going to come in. As I mentioned before, now we may find use for the product property, the quotient property, or the power property of logarithms. And in this case, we're going to find use for the power property. Right? If you have a number multiplied by a logarithm, that number can go inside as a power, right? The exponent that the argument is raised to. So that's what I'm going to write here, right? So this expression on the right, to get it to be just a logarithm and not a logarithm times 3, I'm going to use the power property. Right, I'll just say power there. All right, so now we have, on the left side, still have the log base 10 of 343 equals, and then I put that number 3 that's multiplied by the log inside, and this argument becomes x to the third power. The log of x to the third power. Okay. All right, now I have the equation the way I want it if I want to apply this one-to-one property. Both sides are a single logarithm with the same base. And it's nothing, there's no log times 3 or log times 5 or anything like that. Just like I have up top there in the property. Alright, so now I'm going to apply the one-to-one property. Alright, so by the one-to-one property for logarithms, I'll just put by the one-to-one property. Well, their arguments must be the same. Right? The only way two logarithms of the same base are equal is if their arguments are equal. So 343 must be equal to x cubed. Right? And hopefully you know that the cube root of 343 is 7. So x must be 7. Alright. Now there are other solutions to this equation. Alright, I'll go into some other ones here. Let me show you what I mean. Alright, and don't forget to check. We'll check this in a second. Alright, we'll check the solution later, back in the original equation. But if I have x cubed equals 343, it's a polynomial equation. I subtract 343, right, and then what we have here is a difference of cubes. Right, this is x cubed minus 7 cubed. And remember how a difference of cubes would factor. So this would factor to x minus 7 times x squared plus 7x plus 49. Right, and then we apply the zero product property, right? So either x minus 7 equals 0, or this other factor, x squared plus 7x plus 49 equals 0. And from this one, I'm getting the solution I told you about earlier, right? X equals 7. Or, and then from here, I'd have to use the quadratic formula. All right, x equals, negative 7 plus or minus the square root of 7 squared, all right, 49, minus 4 times 49, right, 4 times 1 times 49, and I'll simplify that in a little bit. All divided by 2a, 2 times 1. And if you simplify that, that's negative 7. Now both these have 49 in common, so plus or minus, and then the square root of 49 is 7. And then you'll have 1 minus 4 left over. If I pull out negative 3, that'd be 7 times the square root of 3 times I, right? That'd be the square root of a negative number, so I have this imaginary unit here. But notice that these two solutions are not real, right? They have an imaginary part. So I'm not going to use them, right? We're only looking for the real number solutions for these logarithmic equations. You should only be plugging in real numbers to logarithms. All right. Okay. So now we check. All right. Now I'll just go back up here. Let's check our solution. Right. The only one I'm going to check is x equals 7. So we have the log base 10 of 343 equals 3 times the log of 7. And if you put the 3 inside using the power property, this is true, right? You have the log of 7 to the third power, which would be the log of 343. You could also pull up a calculator if you want. Okay, and I have a TI-84 Plus emulator here. And let's check, is the left side the log base 10 of 343, which will be between 2 and 3, 2.535 something, is that equal to 3 times the log base 10 of 7? And indeed it is. All right, so my solution of 7 is a good solution, right? It does satisfy the equation. All right. So we check that. Fantastic. And again, always check back in the original equation. Right? Always check in the original. Right? Okay, so then back in the assignment, right, we're just entering x equals 7. Great. Again, if you find imaginary solutions like I did, you're not using those. Right? For these logarithms, we're only going to be inputting real numbers. All right, and after every question, right, there should be a answer explanation. Please read through this. If you get it right, just read through it to make sure you got it right for the right reasons. That you didn't just get lucky. Or, they may go over some alternate method that will help you in future questions that you like. Maybe you like it better. Now, if you got it wrong, definitely read through the answer explanations. Try to figure out, where you went wrong and learn from your mistakes. All right, next question is on the same objective, right? So still using this one-to-one property. All right, so I'm just going to write up the equation they give us here. You have 3 times the log base 5 of x equals the log base 5 of 2,744. Okay. So pulling this up on paper here, and again, here is that, once again, the one-to-one property for logarithms. And just like the last question, yes, both sides have a logarithm, but this left side has another factor that's not a log. There's this times 3. So just like the last question, in order to get this side here to be a single log, I'm going to use that power property. Right. So I'm putting the 3 inside, and then we have the log base 5 of x to the third power equals the log base 5 of 2,744. Okay. Now I can apply the one-to-one property. Right? Both sides are a single log with the same base. The only way two logarithms with the same base are going to be equal is if their arguments are equal. Right? So by the one-to-one property, I'll just write one-to-one here. X cubed, right, the argument on the left, must be equal to 2,744. Alright, so we have to figure out, what to the third power would give me 2,744. Alright. So I'm going to start factoring this off to the side here, 2,744. Now obviously it's a multiple of 2. Alright. And that'd be 1372. Right, 26 plus 144, right? And this is a multiple of 2. That'd be 686. Right, 1200 plus 160, 1360 plus 12 would be 1370. And this is a multiple of 2. 343. And then 343 we saw was 7 cubed in the last question, right? 343 is 7 cubed. So 2 cubed times 7 cubed, this is 14 cubed. 2 times 7 cubed, right? 14 cubed. So the answer here is 14. Right? The solution is 14, right? Taking the cube root of both sides. And then don't forget to check, right? If I plug in 14 for x back in the original equation, and you can punch these in a calculator if you want, just to double check, but 3 times the log base 5 of 14, should be equal to the log base 5 of 2,744. So back in the assignment, right, putting in 14 for our solution. Great. And once again, please, read through the answer explanations. Okay, next question. Alright, so now we're working with the other objective. Use the properties of logarithms to solve logarithmic equations. Alright, so I'm going to write this equation out here. And this one, notice that every term on both sides is a logarithm. Log base 8 of x plus 8 plus the log base 8 of x plus 10 equals the log base 8 of 8. If that's the case, we can use properties of logarithms and then end up using the one-to-one property as well. Right. Okay, so if you look at the left side, see I've got the sum of two logarithms. The sum of two logarithms. Well, if you ever see the sum of two logarithms with the same base, you can put them together and make the log of a product. Right, this is that product property of logarithms. So I'm going to write product for using the product property. So this left side now becomes the following. 2 logs become 1 log. Right, so the log base 8 of, and then the argument of this new logarithm is just the product of the arguments of these logs. So the quantity x plus 8 times the quantity x plus 10. Alright, so now the left side is a single logarithm, and the right side is a single logarithm. just the log base 8 of 8. And now I can use the 1-to-1 property. Right? If two logs with the same base are equal, the only way that's going to happen is if the arguments are the same. Right, so now I'm using that 1-to-1 property. Right? And that means that x plus 8 times x plus 10, right, must be equal to 8, right, setting the arguments equal to each other. And then we're going to solve this. Now this ends up being a quadratic equation. Right, if I multiply x plus 8 and x plus 10, we'd have x squared plus 18x plus 80 equals 8. And then I'll subtract 8 from both sides. We got x squared plus 18x and then plus 72. Right, plus 72. And equals 0. And you can solve this using the quadratic formula, using completing the square. Now I don't know if I can do factoring. 2 times 36, 2 times 4 times 18. Be 9 times 8. You know what, I'm going to solve this by completing the square. It's because we haven't done it in a while. So I keep the quadratic term and the linear term on their own side, and then subtract 72. And then you complete the square. I can complete the square on these two terms because the quadratic coefficient is 1. Remember how to complete the square? You take half the linear coefficient, which is 9, and then square it, and that gets added to both sides. 9 squared is 81. I add 81. Alright, and then this is x plus 9 squared, and then this side is 9. So this was factorable. This was factorable. We have x plus 9 must be equal to positive or negative 3, right? The square root of 9. So x equals, negative 9 plus or minus the square root of 3. So my two possible solutions here are x equals, negative 9 plus 3, which is negative 6, or x equals negative 9 minus 3, which would be negative 12. But don't forget to check. All right, don't forget to check, especially with logarithms. I don't know if you remember, and I'll make this note here off to the side. I had put this up earlier in chapter 10, but you can only take logarithms of positive numbers. So look at what happens when I plug these in. Right? You can only take logs or logarithms of positive arguments, positive numbers. Well, let's put positive numbers like this. All right, and if you keep that in mind, that's going to help us here. Alright, so I'll check the first value, which was negative 6 back in the original equation. So when x equals negative 6, we get the log base 8 of negative 6 plus 8 is 2. And that's fine. That's a log of a positive number. Plus the log base 8 of negative 6 plus 10 is positive 4. And would this be equal to the log base 8 of 8? This works, right? This works. Both the inputs of the logarithms are positive. And if that's happening, that's okay. That's great. You can take logarithms of positive numbers. So negative 6 is a valid solution. And you can use a calculator to check as well. Right, punch in the left side, punch in the right side. Now you could also use the product rule and just say, oh, this is equal to log base 2 of 2 times 4. Log base 8 of 2 times 4, which is log base 8 of 8. Now look at the other solution. The other possible solution was negative 12. Right. If I plug that into the original equation, we have the log base 8 of negative 12 plus 8 is negative 4. Uh-oh. That's bad. That's not positive. That's not a positive number inside the logarithm. So this can't be done. Alright, this can't be done. So negative 12 is what they call, an extraneous solution, but I'm crossing it out. Because when I plug negative 12 in to my original equation, the numbers I'll take logarithms of are not all positive. Right, once again, you can only take logarithms of positive numbers. So the only solution here is negative 6. Okay, so back here, x equals, negative 6 only. Right. Wonderful. And once again, read through the answer explanations. All right, next question. So yet again, I have used the properties of logarithms to solve logarithmic equations. Again, every single term has a logarithm in it. So I should be able to use properties of logarithms and also that one-to-one property eventually and find my values of x that make this a true statement. Okay. So the expression on the left side of the equal sign is a difference of two logarithms, both base 10. And once again, recalling our properties, when you see the difference of two logs with the same base, you can put them together and make a single log of a fraction, of a quotient, right? The quotient property. So I'll write the word quotient here. Alright, and then log minus log becomes a single log. So the log of, and then the first argument is the numerator of the fraction, over, and then the second argument is the denominator. Right, so now the left side is a single log. Right, equals, and the right side isn't yet. Right? The right side has the log of x, fine, but there's a negative 1. Right? Technically this would be negative 1 in front. So I could put that in as a power. And off to the side, just remember that x to the negative 1 would be the same thing as 1 over x. Okay, 1 over x. So the left side, after using the power property, is the log of 1 over x. And now I can use the one-to-one property, right? There are two logarithms with the same base equal to each other. So by that one-to-one property, their arguments must be the same. So this fraction, right, x plus 4 divided by 5x plus 12, must be equal to 1 over x. Right, and if then, this is a proportion, if you just do cross products, you'll have x plus 4 times x equals, 5x plus 12 times 1. Or you could say the LCD was x times 5x plus 12 and multiply both sides by the LCD, and you'd end up with this. X times x plus 4 equals 5x plus 12. And this ends up being some sort of quadratic equation that I'm going to solve, right? Distribute the x here. I have x squared plus 4x equals 5x plus 12. Take everything to the, I'll take it to the left. We have x squared minus x minus 12 equals 0. And this is easily factorable. That's x minus 4 times x plus 3. So my possible solutions are x equals positive 4, that makes x minus 4 0, or x equals negative 3, but don't forget to check. All right, don't forget to check. When I plug in 4 for x, you'd have the log of 8, and I'll do the check over here. Right? When x equals 4, we'd have the log of 8 minus the log of 32 equals negative log 4, right, which would be true. Both sides would be equal to the log of 1/4. Right. So that works. And notice that every number inside a logarithm is positive. So that's good, that's good, that's good. This should be a good solution. All right, so x equals 4 is good. And then the other possible solution was, x equals negative 3. Right, negative 3. Well, if I plug negative 3 in for x, we have the log of 1, which is fine. That's okay to do. Log of 1 is 1 is a positive number, minus the log. Now 5 times negative 3 is negative 15, plus 12 is negative 3. Uh-oh. The number inside that logarithm is not positive, which is bad. You can't do anything with that in this course. All right. So negative 3 is not a good solution. Right. The only solution that works is x equals 4. All right, so back here, x equals 4, and that's all. Great. All right, next question. All right, so now we've been using the one-to-one property all the time here. All right, but we're just asked to use it again. All right, so very similar to a couple questions we've seen in the same objective. Both sides have a log, but not a single, not just a log by itself. Right? This has a log times 3. So I use that power property to make this into a single log. All right, this is the log base 6 of x to the 3rd power on the left. Equals, now the right side is already, a single log. It's the log base 6 of 1,331. And then I can apply that one-to-one property, right? The only way two logs with the same base are equal is if their arguments, their inputs, are equal. So this means that x cubed must be 1,331, which is 11 cubed. So x must be 11. Right, x must be 11. And just as I did in the first example, there are two other solutions to this, but they would have an imaginary number in it. So the only one that works out is 11, and you can check that if you wish, but 11's fine. Right? The log base 6 of 11. 11 is a positive number, so you can actually use it. Right? Great. So x is 11 satisfies that equation. And again, you can use a calculator if you want to check both sides, see if they're actually the same value once you plug in 11. Okay. Next question. All right, so one more like this, one more like this. All right, so very similar, but this time instead of a log times 3, it's a log times 2 on one side. So, we have that single log on the left already, right? The log base 7 of 6,561. I'm putting the 2 in using the power rule, the power property. Right? This is the log base 7 of x squared. Now I have what I want in order to be able to apply the one-to-one property. Right? I have a single log with the same base on both sides. Now the only way these are going to be equal is if their arguments are equal. 6,561 equals, x squared. So this should have two solutions, one positive and one negative, but then we're going to check them, don't forget. Now I could use a calculator, but I'm going to go off to the side and factor this myself. Now I can tell you 9, the sum of the digits is 18, so I know 9 goes into it evenly. Right? And that'd be 9 times 7 for 630, 6,300, sorry. I need a 261. 261 left over would be 29, 729. This is also a multiple of 9. Right, this would be 9 times 81, and this is 9 squared. Geez, okay, so this is 9 to the 4th. 9 to the 4th, which would be as a square. No, it's 9 squared. This is 81 squared. All right. So x here is either positive or negative 81. All right. X equals positive 81. Right, because 81 squared would be 6561, or x equals negative 81, right? Negative 81 squared is also 6561, but don't forget to check back in the original equation. Now when you plug in positive 81, that's fine, right? You have the log base 7 of positive 81 over here, that's okay. You can take logarithms of positive numbers only. So that would work. Negative 81 is the problem, right? If I plug in negative 81 for x, that would give me the log of a negative number. And you can only take logarithms of positive numbers, as I've been mentioning. So the only one that works, back in the original statement, is x equals positive 81. Okay, great. Alright, so that objective's done. We should just have a couple more from the other objective. Alright, so this time, the first two questions I did with this objective, every single term had a log. This does not, right? The two terms on the left are logarithms, but on the right side you just have the number 2, which you can express as a log, but at the moment it's not a logarithm. Alright, so how do we approach this? Well, again, very simple, very simple. And I hope you remember how to transition between logarithmic form and exponential form. That's going to be key. Alright, so on the left side, I can make a single log, right, to get fewer terms, right? The fewer terms in an equation, usually the better. So I can use the product rule because this is the sum of two logs with the same base. So this becomes a single log, right, the log base 2, of the product of these arguments. So x times the quantity x minus 3. Right, all of that inside the log, the product. And then I have equals 2. Now, you could express this as a logarithm as well. 2 is the log base 2, right, with the same base as I have on the left side. I want that. 2 is the log base 2 of 4. All right? But say you didn't see that. Well, remember, if you have a single log equal to a number, then you can very easily get to the variables, get to trying to solve for these variables inside the log by changing to exponential form. But first you need it like this. You need a single log equals a number. You need it this way to be able to then change to exponential form. Alright, so remember what this means. If the log base 2 of x times x minus 3 is 2, that means that 2 to the second power, right, 2 to the second power equals this argument, equals x times x minus 3. Once again, I am hoping you remember this from previous sections. Right? This has been discussed before, changing back and forth between logarithmic form and exponential form. Well, this is just x times x minus 3. I'm just switching sides here. So moving that to the left side equals, 2 squared is 4. And then I'm solving this equation. So distributing this x, we have x squared minus 3x equals 4. Subtract 4 from both sides. Now I can use the quadratic formula, or just factoring. This one's again easily factorable. Factors to x minus 4 times x plus 1. And so my possible solutions are positive 4 or negative 1. But don't forget to check back in the original equation. So if x was positive 4, we'd have the log base 2 of 4, which is okay to do, right? As long as the number inside the logarithm is a positive number, you're fine. And then over here, when x is 4, log base 2 of 1, totally good. Right, so both of those are good. X equals 4 should be a valid solution, and you can test it with a calculator if you wish or whatever. But negative 1 is not good. Alright, because if I plug in negative 1 for x, right away I'm taking the log base 2 of negative 1. The number inside the logarithm is not positive, so that's bad. Right, so negative 1 is not a valid solution. So the only one that works out in the original statement is x equals 4. And if neither of them worked, right, because you notice in some of these they're asking you to enter that empty set symbol as an answer if there's no solution, that could happen. Right, if you go through solving these equations and you check your solutions and neither of them work or none of them work, well, then it just has no solution. Or you did something wrong. But if you did everything right, if you feel it, and nothing works, there's no solution. Right, so x equals 4 is the only one that works here. Alright, and then I should just have one more of these. Alright, and one more time, we're back to an example where every single term is a logarithm. If that's the case, then we can apply that one-to-one property eventually, right? Once I write both sides as a single log. Okay, so on the left side, we've got the difference of two logs with the same base. So that I can use that quotient property, make that a single log of, the numerator will be the first argument, x plus 2, divided by, and then 4 times x plus 8. Well, you can leave it this way if you wish. Alright, let me show you. We have log of x on the other side. You can leave it this way if you want. Okay, and use the one-to-one property. I have two logs with the same base equal to each other, so I can set their arguments equal. So x plus 2 divided by 4x plus 8 must be equal to x. And then I multiply by 4x plus 8. We get x plus 2 equals x times 4x plus 8. Then distributing this x here, we have x plus 2 equals 4x squared plus 8x, and then taking everything to one side, we'd have 0 equals 4x squared plus 7x, right, plus 7x, and then minus 2. Right. And then you can use the quadratic formula, x equals just make sure I got this right here, 8x minus x, 7x minus 2, right? So negative b, right, negative 7 plus or minus the square root of b squared, 49. And then, 4ac is negative 8. A times c is negative 8 times 4 would be negative 32, and then you're subtracting that, so it'd be plus 32. and all this divided by 8, right? And yeah, here we go. We got negative 7 plus or minus. Now this is the square root of 81. That means this was factorable. I should have been able to factor this. I didn't check that. That's 9, right? It's 49 plus 32 is 81. Square root of 81 is 9, and then all this divided by 8. So my two possible solutions are x equals, negative 7 plus 9 divided by 8. That's 2 divided by 8, which is 1/4. Or x equals negative 7 minus 9 is negative 16 divided by 8 is negative 2. And when you check these, 1/4 is fine. Right, if you plug in 1/4, you'd have 2 and 1/4, 2 and 1/4 inside this log, that's a positive number. You'd have 9 inside this one, that's a positive number. You'd have 1/4 inside that log, that's a positive number. As long as all the numbers inside the logarithms end up being positive, and you know you did everything right, that should be good. X equals negative 2 is bad though. If I plug in negative 2, we'd have the log of 0, which is undefined. Right? That 0 is not a positive number. So negative 2 is a bad solution, an extraneous solution. Yeah, so after all that, the only solution here is positive 1/4. Now, you could have just done this as well. Right? Or, x plus 2 divided by 4 times x plus 8. Well, 4 times x plus 8 factors to 4 times the quantity x plus 2. And you see the cancellation of x plus 2. So I end up with the log of 1/4 after simplification equals the log of x. And then I can use the 1-to-1 property and say, oh, x must be a quarter then. Right, 1/4 must be the same as x, and check your solution and it works. Great, that would have been a much easier way of doing that, of course, but either way is fine. Either way is fine, as long as you're checking your solutions back in the original equation at the end, and remembering that you can only take logarithms of positive numbers. All right, positive 1/4 does that. Great. And once again, please, read through the answer. Oh, they did it. They did do it the long way. All right. But please read through the answer explanations. All right, and that should do it for this version of this assignment. Now, as I said at the top of the video, please understand that the questions I saw here may not be the same questions that you see when you do the assignment, but the objectives are the same. The types of questions, how you would do them would be similar. So I'm hoping that watching me go through these 8 questions here helps you in some way when you're working on the assignment on your own. And thank you very much for watching.